A semiconductor is a poor conductor, semiconductor, but it's really more exactly, a better definition of it would be a poor insulator. It's not a very good insulator is what a semiconductor is. So 19th century scientists, and really there isn't any difference between insulator, semiconductor, and metals. They're all the same things. Similar things are happening. Just because of the quantum mechanics, some things can move electrons more easily than others. So the 19th century scientists knew that as temperature increases, metal conductivity decreases. They knew that, and they could measure it. It was one of those obvious, easy things to measure, was the voltage drop across a piece of metal as you change the temperature, because they could heat it up and cool it down, and they could see what's happening. And that could be quite easily explained by classical physics, classical mechanisms like particles banging into each other, and as you heat it up, the particles bang more into each other, and there's more and more particles to be banged into, and more random motion, and it's harder to get particles through it. And if there's particles carrying electricity, then that would explain it. And they could also just say, well, insulators just don't conduct. So they could measure the conductivity of glass, and they say, well, it just doesn't conduct. So everything was pretty simple and straight. But they could not understand semiconductors, because when you heat a semiconductor up, it conducts better. And they could not, you can't explain that. No, I don't want to do that. All right, so it took quantum mechanics to be advanced enough by about the mid part of the 20th century, mid-third of the 20th century. So by the 20s and 30s, 40s and 50s, it took that long to really understand the quantum mechanics well enough to understand and explain how and why semiconductors work the way they do. And by understanding that, they could also understand insulators, and they could understand metals. So it actually all started to make sense. For a lot of things, quantum mechanics is just a correction to the regular mechanics. Well, it is just a correction to the regular mechanics. And at room temperature and physical size that we're used to, it doesn't make any difference. But on the scale of an atom, it does make a big difference. And so by understanding quantum mechanics, they could explain how it works, but we're not going to do the quantum here. So that's for starting at 12:25 or 12:15. So basically, a semiconductor like silicon, if we represent a silicon atom, it's got 4 electrons in its outer shell. And so its valence is 4, and a full shell is 8 electrons. So something like neon has 8 electrons in its outer shell, 2, 4, 6, 8. So neon feels like it has a full outer shell, and it doesn't want to bond with anything. It'll only bond with itself by weak van der Waals bonds as a liquid and things like that. It really doesn't bond. So for the case of something like neon, basically no chemistry. But silicon has 4 free electrons and lots of chemistry that it can do. In fact, carbon is the same structure. Carbon has 4 free electrons, and those electrons, the bonding energies are a bit higher with carbon than with silicon, and so carbon does an enormous amount of chemistry. All of organic chemistry is carbon-based bonds, and silicon bonds in very similar ways. Just it's not as strong and doesn't survive in our sort of world the way that carbon-based chemistry does. So a full outer shell is 8 electrons for anything beyond helium, and in the periodic table. And an atom wants to feel like it's at it wants to feel like it has a full outer shell. That's the lowest energy condition for atoms to be, is when they have a full outer shell of 8 electrons. But they don't want to have more electrons than they have protons, so they want to have an electrical balance. That's important also. If they can feel an electrical balance, but also feel like they have 8 electrons in their outer shell, that's the lowest energy configuration for an atom. And that's what a crystal is. A crystal is a 3-dimensional arrangement. I will draw a crystal as a 2-dimensional arrangement. But a crystal is a 3-dimensional arrangement of atoms that each atom feels like it has 8 electrons in its outer shell. And so if I draw the electrons as red, there's and at the edge of this fake crystal, this 2-dimensional crystal, there's some dangling bonds. So if you look at, for instance, this atom right here, it feels like it has 8 electrons surrounding it, because it's sharing an electron with this atom, and it's sharing an electron with this atom, and it's sharing an electron with this atom, and it's sharing an electron with this one. So it doesn't have full ownership of those 4 electrons that it's sharing, but it feels like it has them in its outer shell. And so it feels like it has a full outer shell. And that's a low energy configuration. And there will be a distance and an arrangement depending on those molecular orbitals, those atomic orbitals. There will be an arrangement that every element feels most comfortable in. And for silicon, it's a diamond lattice, a diamond crystal shape, same as carbon is. But I can't draw that. It's a complicated structure in 3 dimensions. So I will draw a 2-dimensional fake crystal here, showing 8 electrons around each atom. Now it's important, if you look kind of far enough out, you'll see exactly the same number of electrons as you have protons. So there is no electrical imbalance. But each atom will feel like it has the proper number of electrons in its outer shell, which is 8. Now, if we could cool this crystal to absolute 0 degrees K, if we could cool it all the way down to there, then each electron would be exactly where it's supposed to be, and nothing would be jostling around or moving. Everything, it would be in its absolute lowest possible energy state in this crystal. And anytime it's not in this crystal arrangement, it's at a higher energy state. And if we bounced around enough, some of these electrons can actually get knocked off. So as we raise the temperature of this crystal, this atom is moving around, and it starts to move a little bit more, and this one starts to move a little bit more. And each of these electrons, they're always moving, even at absolute 0, but they're moving in a regular ordered way at absolute 0, but they've got a little more random motion as we heat them up. And as we heat them up and up, for instance, in the case of silicon, after we get up to about minus 50 degrees C, something like that, they're really moving a lot. I mean, a lot isn't very much. It's, a 1,000th of a nanometer or something like that they're moving, but they're moving. And some of that energy, once in a while, is going to cause an electron to get boosted to a higher energy state. That means there's 8 possible bonding sites, but we don't have enough electrons for all 8 of those bonding sites because they're shared, right? We're sharing energy states with these surrounding atoms. So there's 8 possible states here, but we only have enough electrons to fill 4 of them. And at the lowest possible energy, those 2s and 1p, p1, p2, whatever it's called, will be filled, the very lowest possible orbitals. But if we raise the temperature some, one of these electrons could get boosted to a higher orbital. That's exactly the same thing when you think about chemistry, about the the lines that show up from a hydrogen atom when you heat it up and let it cool down. You see light emitted with certain energy levels. It's exactly the same concept because an electron was boosted to a higher orbital, and when it came down, it gave a certain amount of energy and gave off light corresponding to it. Now, if it happens that an electron gets boosted up to a little bit higher energy state, say if this electron, which was poorly drawn anyway, if we had an electron there that got boosted up to a higher energy state, it could be that it wanders over here and it occupies a place right there. It's kind of temporarily stuck over there, and it could occupy a higher energy state, which might be over on this atom over here. It used to be here. This is where it belonged. That's its lowest energy location, is in the lowest energy orbital, but it could get moved over here and occupy a higher orbital there. Now, of course, there's a charge imbalance here, right? We've got one too many electrons here compared to back here, right? So there's actually an extra electron, and I'm saying that electron is moving around. It can move off, and if it's free to move around, then if we put an external electric field, this electron will keep moving with that electric field. And if we put a positive charge over here somewhere, this electron will tend to want to go that way, and it'll conduct current, and it'll keep moving. Now, back here, there's a missing electron. And so that means we have a net positive charge, right? There's not enough charges to balance the protons in that nucleus, and so there's an extra positive charge right here where that electron left, and there's a net negative charge over here. But we really don't know. So I might be kind of inferring that these electrons have serial numbers. They don't. We don't know where an electron really belongs. We just know where it came from, maybe. But once it's over here, we know that there's 9 electrons around here. We don't know which is which. And this extra electron, it just means there's an extra electron. It's got some probability of moving off somewhere else. And under this influence of an electric field, it would. And it's also possible that, say, this electron here could hop over here and fill that. And if this electron in this spot, let's say first this one moves. So we get this positive charge move down here, and then it might move over here, in which case we now have a missing charge over there, and now we have this positive charge over here. It's as if there's a positively charged particle. It's not, it's a missing electron, but we could track that positive charge, that missing electron, we could track it around in that crystal and say, oh yeah, there's this positive charge that keeps moving. It's as if there's a particle which is a positive charge. And we call that a hole. And it has a positive charge. And it behaves just like an electron, except it behaves as if it's a little bit heavier than an electron. So it's a little harder to move around. It's got a little more momentum than an electron, but it behaves just like an electron, except that it's got a positive charge. So if we put a negative plate on one side of this, if we put a negative plate over here, if we had a negative plate and a positive voltage, then this electron will tend to be attracted there, and this hole will tend to be attracted to that negative voltage because it's got a positive charge, so it's attracted to the negative, and the electron with its negative charge will tend to be attracted to that positive. Now, in 1 cubic centimeter of so in 1 cubic centimeter of silicon, so if you imagine a little block That's a little too small. On my iPad, that might be 1 cubic centimeter. In a little box of silicon that's 1 centimeter per side, it's 2 times 10 to the 22 atoms in that little block of silicon. By comparison, there's 1e to 9 grains of sand. Cubic centimeter of silicon has a lot more electrons in it than 1 cubic meter of sand has grains of sand in it. In fact, it's 13 orders of magnitude more. It's a huge difference. It's a stunning difference. There's a lot of electrons in a chunk of semiconductor, like silicon. Now, at room temperature, 1 cubic centimeter of silicon has something like 1.5 times 10 to the 10 free electrons per cubic centimeter. So when I say that every now and then an electron will get knocked off the lattice like this, knocked off its place, and is free to move around, and then when it creates a hole, every once in a while that happens. It's really, really just once in a while. At room temperature, a cubic centimeter of silicon has only 1.5 e to the 10 free electrons per cubic centimeter, right? As opposed to 2 e to the 22 atoms per cubic centimeter. If I make a fraction of that, then we have if we look at the free electrons divided by the number of atoms, should I say? Then this equals a fraction that's 7.5 e to the minus 13. I don't even know what that number is, right? It's 10 billion, something like that. It's a really big number, a tiny number, a tiny fraction of all the possible silicon atoms actually have lost their electron, and it's off moving around. It's a tiny, tiny number. It's something like 0.1, 2, 3, 4, 5, 6, 9, 10. Right? It's some tiny percentage actually have a free electron. But that's enough. If we put a voltage on a chunk of silicon, it's enough to cause those electrons to move, and it's enough for us to sense a current, because we can sense current really well. And if we put a big enough voltage, we can definitely see it. And in the 19th century, scientists could do that. They could do that experiment. They could put a voltage on a chunk of semiconductor, and they could say, oh, yeah, this thing conducts. And then they could put it on the stove and go, wow, it conducts even better. This is wacky. And it just, freaked them out. It's like, we can't explain it. Now, when we make a free electron, by thermal energy, we also make a free hole. I'm going to say it has a plus charge. I'm going to stop writing that at some point. But we make a free hole, which has a positive charge, and it can move around. Remember, a hole is a missing electron. So there's a place in the lattice that is missing electron, but other electrons can fill that, and then that missing electron can move around. So every time we make a free electron by thermal energy, we also make a free hole. They're made in pairs. So we can say an electron hole pair. And conduction will occur due to both the electrons and the holes. So we'll get current flowing because we move electrons to the positive side, and we'll get current flowing because we move holes to the negative side. Both of those will occur. So that's kind of nice. You say, okay, we get double the number of current, but doubling this tiny number doesn't really change it much, right? It becomes 1.5 e to the minus 12 or something. It's still a tiny number, right? Even though we doubled it, because we multiplied by 2 instead of raising it to a bunch of orders of magnitude. So all by themselves, a semiconductor is a pretty lousy conductor. It's not a very good conductor. So compare with iron. Iron has 8 e to the 22 atoms per cubic centimeter, and it has 8 e to the 22 electrons, which are free to conduct, per cubic centimeter, because every atom is able to give an electron to move around. So compared to silicon, for a semiconductor, iron is a fabulous conductor, even though we know iron isn't really all that good of a conductor. It's nothing like copper and silver and aluminum and stuff. Iron's pretty lousy. We don't want to build the wires in our house out of iron, out of steel, even though it's cheap, right? We'll put copper, which is really expensive, in our motors and in the wiring in the house because it's so much better at conducting than iron is. Yet iron is obviously way better than silicon. In 1 cubic centimeter, 77 to the minus, some huge number compared to 8 e to the 22. Yeah. Well, we'll use semiconductors because we can make transistors out of them. And in fact, we can't make transistors out of iron. So there's some important properties that I'll get to in just maybe today that help you be able to make a transistor. So we call a pure semiconductor. We call that a pure semiconductor an intrinsic semiconductor. So we call that the intrinsic case. If we have a pure, perfect semiconducting crystal, we can call that intrinsic. And those free electrons and holes made by only thermal energy are intrinsic electrons and holes. That's just it's kind of some bookkeeping. So we call it intrinsic silicon, for instance. So we can look at the number of electrons in a chunk of semiconductor. It's usually better to normalize it by the volume. So to find the density or the number of electrons per cubic centimeter, for instance. That would be the electron density. We could count the number of electrons that are free. We could count the free ones, but it's easier to say we have this many free ones per cubic centimeter. It'll make it easier to talk about transistors, and we don't have to worry about how big the transistor is anymore.
And transistors come in all sizes and shapes, so it's useful. And the density of holes, free holes, too many letters there. So we could talk about the number of free electrons per cubic centimeter and the number of free holes per cubic centimeter. And for intrinsic, for the intrinsic case, those numbers are equal because every electron makes a hole, right? Every thermally generated electron makes a hole. And at room temperature, for silicon, and I always talk about silicon, I talk about silicon almost interchangeably with the word semiconductor because the vast majority of our devices are made out of silicon. So if there's, you know, a few 100 trillion transistors in this room, there's maybe a few hundred that are not made out of silicon, literally. So the vast majority of our transistors still are made out of silicon. And so I talk about semiconductor and silicon almost the same. That may change at some point. But at room temperature for silicon, N is equal to P is equal to 1.5 e to the 10. We usually just say centimeter cube per centimeter minus 3 centimeter per centimeter cube. So that's that number I gave before. And that's the intrinsic carrier concentration. Now, if you're confused because I have N sub I here, and I've got N here, it's like this N over here. God, that lag is just ridiculous. And this N sub I down here, those are different. Those N's are different things. Here it means intrinsic carrier, and over here it means free electron. And the concentration is the same as the free holes. It's by, you have to learn this by context and just deal with, you understand Ni means electrons or holes, and N and P means electron or holes. They mean different things. It's just a nuisance. You deal with it the same way you deal with TO versus TOO versus TWO. When I say 2, you don't actually know what it is I'm saying. Am I saying TO or TOO or TWO? And you figure out on your own which one I mean. Now, if it's in the middle of a sentence and I say there's 2 days left this week, you know exactly, well, that's TWO. If I say we need to go out of this building too, then you know, oh, that's TOO. And if I say it's time to go to another room, you know that's TO, because you heard the context that was used in. In the same way, you have to understand what this is by the context. It's just it's a nuisance. That's how it is. So the remarkable thing that we can do with a semiconductor is we can dope it. We can add some impurities, and if we add just the right amount of impurity and just the right type of impurity, some interesting things can happen. So silicon has, write that down below. Silicon has 4 electrons in the outer shell, and boron has 3 electrons in its outer shell, and arsenic has 5 electrons in its outer shell. And as it happens, we can squeeze a boron or a arsenic atom into a silicon crystal lattice. And when we do that, we brought in either one fewer electron or one extra electron, and that causes all kinds of interesting things to happen. Drawing my electron bonds without glasses here, I can't see it actually. So this would be a pure intrinsic crystal, two-dimensional, that I'm drawing. And every silicon atom in orange has the feeling of 4 electrons in its outer shell. Now, if we replace one of these silicon atoms, so if we put, for instance, arsenic there, say we have an arsenic atom we put right here, it brought an extra electron to it. Now that electron wants to stay close to that arsenic atom due to the charge balance, but that means that it would be in a perfectly normal shell, orbital shell, in orbital for that arsenic atom. But for these surrounding silicon atoms, it's kind of odd and not normal. So we added an arsenic atom and it added an extra electron. And it turns out that it's quite easy. It just takes a tiny, tiny bump of energy to bump that electron free of that location and let it wander off. And so it's quite easy for it to move off and be a free electron. That electron from that arsenic atom, quite easy for it to just get up and move off and be free. And if it sees a positive charge somewhere, it'll be attracted to it and move there and carry current. Now, when it left behind a positive charge. So if it's gone, I'll erase it. It's left behind a nucleus that's missing an electron. But that's a nucleus, it's protons. It's a bunch of protons, they're stuck. They can't move. So it left behind a fixed charge. As it made a free negative charge that can move around. So that's different from the intrinsic case when we have an intrinsic semiconductor. If we heat it up, we may make both equal numbers of electrons and holes that can both move around. But when we dope it, for instance, if we add some arsenic to a silicon crystal lattice, we will make an extra electron that can move around, but we won't make a hole that can move around. So we made more electrons. So heat makes equal numbers of electrons and protons that are free to move around. And there's something like 1.5 e to the 10 per cubic centimeter of those. And if we add an impurity such as arsenic, we can add something that has an extra electron that could move around free, but it doesn't create an extra hole that moves around. So we've only added extra electrons. But the charge, if we look around this whole chunk of semiconductor, the charge is still balanced, right? We still have the same number of electrons as we have holes if we look far enough away. Now, if we did the same thing with boron, make my fake two-dimensional crystal again. We put boron in this crystal lattice. We've added an element that only has 3 electrons in its outer shell. That doesn't have enough. Neighboring silicon atoms are going to want to have more. All right, there's going to be something missing. And what's missing, they can fill easily. So we'll add boron. Just let me erase one there. And when we add the boron, there's a missing electron, right? There should be an electron. See if I can make this pointer point. Man, that's slow. There should be an electron right there. It'll come up eventually. There it is. There should be an electron right there, right? But it isn't. It isn't there. But this silicon atom over here could send its electron over there, and now there'd be a missing electron over here. So it could be that this electron could flow over there. Oops. And if that happened, we would have an extra electron right there. And we would now have a missing electron for a hole. It's moving. And as those electrons fill that hole, there becomes another missing electron somewhere else. And we get a free hole that can move off. A free hole that can move around with a positive charge. But it leaves behind a negative charge. All right. It leaves behind a nucleus that has a negative charge that can't move around. And so by doping, we can add more electrons or more holes to that crystal lattice without changing the charge balance of everything that's there. And I yacked enough that that's where I need to stop, I guess.